All right. So you should have this page, exact zeros. All right, and you need your calculator. We're going to use our calculator as an aid, but not to help us with everything, because we can't use it for everything. Because the objective here is to find the exact values for all of the zeros of a polynomial function. So Friday we talked about the degree. So this polynomial function that they give me right here is to the fourth degree. So how many zeros should it have? 4. It should have 4 because it's to the fourth degree. So I can plug it into my calculator, and I can look to see if there are all 4 zeros. Now, they've already done that, so they put the picture right here. So I can see there are 4 zeros. There's one right here, 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 and here. Here is the problem with those 4 zeros, though. If you do a second trace to find those 4 zeros, this one comes out really nice. X equals 3. That's a rational zero. Rational means a nice number that can be written as a fraction, a nice fraction. But when I go to find this zero, look at what I get. 0.236066798. That is not a nice rational zero. It is not exact. We want to find the exact zeros. This one is not a rational zero. Now it's real because we can see it. Remember, we've talked about when we say non-real or imaginary, we don't mean it doesn't exist. We mean it's not an x-intercept. I can see all 4 of those. They're all 4 real, but some of them are irrational. They're nasty decimals like this. I want exact zeros. When they come out to be decimals, I'm going to have to use the quadratic formula instead because I want an answer that has a radical in it and is written as a fraction with a radical, not a decimal that never ends and never terminates or never repeats. So, a couple of things we can do. We can go to our table and we can look for zeros on the table. If you look on the table and you don't see the zeros, you might notice something like this. If you look at the first picture they gave you, right here it goes 540, positive 544. And then right below that is negative 91. Now think about that for just a second. On the y values of a graph, I have to go from positive 544 to negative 91. If you did that on a graph, if you took your pen and you went from positive 544 down to negative 91, what has to happen in order for you to get from a positive y to a negative y? You have to cross through the x-axis. Which means there has to be an x-intercept between negative 5 and negative 4. There's no other way to get from a positive to a negative. So what they did here was, okay, well, if there's got to be a 0 between those, so let me change my table setting. And this time they changed their table setting to count by 0.5. They did a delta table, you change the table setting, and count by 0.5s. And you still can't see a 0. So they changed it again to count by 0.25. And when they did that, you could see a 0. So sometimes we can adjust our table and still find rational zeros. Negative 0.75, that's negative 3/4. That's rational. It's only irrational when it is a decimal that we cannot convert to a fraction. So they found it to be negative 3/4. All right, so problem is that may not be all of them. So down here it says from the list of possibilities. So you guys are fortunate that you get to use a graphing calculator. I will allow you to use a graphing calculator, and often I will tell you what one of the zeros are because I don't want to spend all day with you looking for zeros. However, there used to not be graphing calculators, and even when I was in college and we had graphing calculators, they were outrageously expensive, so we didn't have them. So when we had problems like this, there was no way for us to just plug it in our calculator and look at the graph and go, oh, there's a 0, and there's a 0 that bounces, and there's another 0. We couldn't do that. We just had to start picking numbers and synthetically dividing until we found zeros. Now think about that, how long that might take. Yeah, it would take a long time. It would totally stink. So some mathematician figured out we can narrow down the possible zeros by using the numbers in our problem. So that's what the rational root theorem is. It says that if I put P over Q. We're going to use both the positive and the negative version of P and Q, where P is the factors of the constant. Now that only helps me if I know what a constant is. What is the constant in a polynomial?
The number that doesn't have an x or an x.
Perfect. It's the number that does not have an x or an x squared. As long as there's no x with it, it's the constant. So we're going to take the factors of the constant, and we're going to put those on top of the factors of the lead coefficient. And that's going to give me a list I can choose from. And then I can choose from my list and start synthetically dividing. And then it's not quite as tedious as just choosing out of the sky. All right, so we're going to use our rational root theorem. It's the same polynomial from the front of the page. They only listed part of it here because all I need are the constant and the lead coefficient. So I'm looking for the factors of 9. That's my constant. Factors of 9 are 1, 3, and 9. 1 times 9 and 3 times 3. So that's all the factors of 9. And then the factors of 4, that would be 1, 2, and 4. 1 times 4 and 2 times 2. All right, so far so good? So we factored the constant, we factored the lead coefficient. Now we have to put them into those fractions. So it says zeros, question mark. That's because these are not the zeros. This is our possible list of zeros. We're hoping that there's a zero here. So I'm going to take P over Q, so 1 over 1, and it's both the positive and negative version of that. 1 over 2, positive and negative. 1 over 4. 3 over 1, 3 over 2, and 3 over 4. And because it's both positive and negative, it doesn't matter if your constant or your lead coefficient are negative, because when we make our list, we're going to put a plus minus in front of all of them anyway. So don't worry about whether it's positive or negative. And then last I had 9 over 1, 9 over 2, and 9 over 4. All right. So now I've got a list to narrow things down. Now, that's still a lot. That's still 18 numbers to choose from. But 18 is a whole lot better than infinite. So if this was back in the day, we would have just started, and I would have said, okay, I'm going to try 1. And I'd have plugged 1 in, and I would have synthetically divided, and it would have not been a 0, and I would have said, okay, let's try -1. And then we would have just kept going until we found them. Lucky for you, you have a calculator, and we can look in the calculator, and we can see that 3 is 1. So we synthetically divide. Now, listen, this was a confusion in a couple of classes earlier today. I need the zeros, because what degree is this polynomial? Right here. What degree is this polynomial?
3.
It's the 4th degree. Can you use the quadratic formula when something gets to the 4th degree? What degree does it have to be in order to use a quadratic formula? It has to be squared. So I have to go all the way down from a 4th degree polynomial to a cubic to a quadratic before I can use the quadratic formula. And I have to use the quadratic formula to get exact answers. So I need to use the zeros that I've found. That's what we're doing. So here's my polynomial. They set up the coefficients. And then I looked on the graph and said, okay, 3 is a 0. I'm going to synthetically divide with that, which they did, and got a 0, which they should have. Then I used the new coefficients, and I'm like, okay, I had another 0 I could see on the graph. It was -3/4. So I used those new coefficients. I used my other 0. I synthetically divide, and now I am down to a quadratic. Once you get a quadratic, you can use the quadratic formula to get your remaining 2 zeros, which they're written right here. They wrote them all out right here. They simplified it. You have to simplify that. Because 16, 8, and 8 are all divisible by 2. So they divided them by 2 and got these 2. So there's all 4 of the zeros. 2 of them are rational, 3 and -3/4. These 2 are irrational. They're real, we could see them on the graph, but they were nasty decimals. So I had to get the rational versions. So that's what we're doing. Okay? Are y'all sort of okay a little bit? I promise it gets a little easier when we do one. So let's look at this first one. First thing we're going to do is make our list. So we're going to factor the back number. So I'm factoring 30. Factors of 30 are 1, 2, 3, 5, 6, 10, 15, and 30. or this was at least nice. The coefficient is 1. What are the factors of 1? 1. So when I set this list up, I don't actually even have to set the list up because it's just 1 over 1, 2 over 1, 3 over 1, 5 over 1, 6 over 1, 10 over 1, and 15, and blah, blah, blah.
Yeah.
Plus and minus. All right, so that's where I am looking for my rational zeros to be. So now I'm going to plug it in my calculator and see if I can see any of them. While I'm plugging it in, so it's x to the third power, how many zeros should I have?
3.
There should be 3. So let's see. All right, so I plugged it in to y equals, and I hit graph, and this is what I get. How many zeros do you see?
3.
And look at them. These cross very nicely right on grid lines.
Pretty awesome.
Yeah, it's so nice when that happens. It really makes your life much easier because this means I have a 0 at, this first one looks like it's at x equals -3. And then x equals 2. And x equals 5. Now I'm going to check just to be sure that that's where they are by going to my table. Listen, always look at the graph first. I'll tell you why on the next one. Okay, so let's see, -3. Oh, my graph. Hold on, let me change my table is counting by something crazy. Okay, so let's see. -3 is in fact a 0. And then 2 is a 0. And 5 is a 0. So that's the zeros. Then it says, describe the number and nature of the zeros. Well, we already said there's 3. They are all rational because none of them have a radical. None of them are those nasty decimals. 3 rational, real, because I could see them on the x-axis, roots. If you can see all 3 on the graph, on grid lines, just like that, that's all you have to do. You don't have to do anything more complicated than that. They won't all work out that way, but when they do, don't waste your time doing stuff you don't need to do. Okay, on the second one, same thing, we're going to make a list. So I need all the factors of 64. Real quick trick, if I haven't already told you this, some of you are already told it now. If you are not the best at factoring a single number, you can put that number in the calculator in y equals, divide it by x, and then if I go second and graph, or go to the table, any whole numbers are factors. So 1 and 64, 2 and 32, 4 and 16, 8 and 8. That's all the factors of 64. So it's a quick way if you need to get factors. And then factors of 1 are 1. So again, that's my list. I'm going to go to y equals and plug it in. How many zeros should I have? There should be 4.
What about 1-to-1 thing?
1-to-1 means that both the original graph and its inverse are functions?
Oh, okay.
Is that what you're asking?
I grab all of the factors.
Oh, no, that's the second, that's the lead coefficient. 1. The lead coefficient is 1, the factors of 1 are 1. Okay, so I'm going to hit graph. Always look at the graph first. All right. How many do you see?
2, 3.
3. But what can you tell me about the one on the far right?
The bouncer, so it's squared.
It bounces, so it's squared. So really, you see all 4. So the one on the far left is -4. So I got x equals -4, -1, and 4. And even though I'm only listing 3, there's a reason why I'm listing 3. I have 2 distinct real rational roots and 1 double real rational root. That equals 4. 1, 2, 3, 4. Are we good? doesn't matter, remember, because we're gonna put plus minus on all of them anyway. 1, 2, 3, 5, 6, 10, 15, and 30. This time, it's the factors of 2. So 1 and 2, which means my list is a little longer. Because I got positive and negative 1, 2, 3, 4, 5, 6, 7, or 1, 2, 3, 4, really? 1, 2, 3, 5, 6, 10, 15, and 30. But I also have 1 half, 2 over 2, 3 halves, 5 halves, 6 halves, 10 halves, 15 halves, and 30 halves. So, all right. So let's plug it in the calculator. How many roots should you have? 3. All right, I always want to look at the graph first to see if any of them bounce. I got no bouncing here. And I have another issue. None of them cross on grid lines. But I'm hopeful that some of them are still rational. And I don't want to do a second trace and trace them all because that takes forever. Another thing that you can do, if you go to second and table setting and change your delta table, if you'll always do it as 1 over A, with A being the lead coefficient, my lead coefficient this time was 2. So if I do 1 divided by 2, it should hit every rational root in the table. Now you may have to scroll a long way, but, oh, there's one right there. I see it. 2.5 is a 0. Now, I know that you were tempted to do 2.5 because y'all love decimals, but don't. I promise you it's easier as a fraction. 2.5 as a fraction is 5 halves. I'll show you why it's easier as a fraction in just a second. All right. Now, I can scroll my table, and you're not going to see any more roots on that one because the other 2 are not rational. So they won't show up on the table. So we're going to use the one rational one that we have, and we're going to synthetically divide. So I'm going to set up my coefficients. 2, negative 21, 52, and negative 30. I use the 0 that I know, 5 halves, to synthetically divide. All right, has everybody have it set up?
Yes.
All right, so remember the first step of synthetic division is to drop that lead coefficient. And after you do that, you multiply. Now let me write this out to the side and let me explain why it's easier to use a fraction. Because if you write this out, 5 halves divided by 2, that's also the same thing as 5 divided by 2 times 2. And in PEMDAS, multiplication and division happen at the same time. So this is way easier to divide and then multiply. Listen, don't put it in your calculator. I want everybody to stop because you can do this in your head. What is 2 divided by 2? 1 times 5? Okay. See what I mean? Add straight down. Negative 21 plus 5 is negative 16. In your head, negative 16 divided by 2. Negative 8 times 5. Negative 40. Add straight down, and you get 12. Divide first. 12 divided by 2. 6 times 5. See what I mean? You didn't have to do anything in your calculator. You can do it all in your head. Fractions are so much better than this.
That's pretty dope.
All right. So remember, this was to the 3rd degree. So what degree is this remainder stuff? Should be squared. So that would be 2x squared minus 16x plus 12. Anybody notice anything about all those numbers? Yeah, go ahead and divide them by 2. So you get x squared minus 8x plus 6. Anybody think of any factors of 6 that would add to give you 8? Factors of 6 are just 1 and 6 and 2 and 3. Any of those add to give you 8? So we have to use the quadratic formula. The quadratic formula is negative b plus or minus the square root of b squared minus 4ac all over 2a. All right, so negative 8 plus or minus the square root. Negative 8 squared minus 4 times 1, 6, all over 2 times 1. Simplify. Let's see. So that's positive 8 plus or minus 64 minus 24. Square root of 40 breaks down. You can go off to the side and break it down if you need to. There's several that I just know off the top of my head. It's 2 square root of 10. Now all of my outside numbers can be divided by 2. So I do that and it gives me 4 plus or minus square root of 10. So I have one real rational root at 5/2. And then I have 2 irrational roots, 4 plus the square root of 10 and 4 minus the square root of 10. So that's all 3 of my solutions right there. All right, y'all sort of doing okay a little bit, kind of? All right. So on number 4, it says first, use your calculator to find the 2 rational zeros. So we're going to put it in our calculator. It tells me there were 2 rational ones, so as long as I put it in correctly, I should be able to see 2 of them on my graph. Okay, so I see 1, 2, 3, looks like -4. -4 is one of them, and 2 is the other. So x equals -4 and 2. Those are the 2 rational ones. The other 2 are irrational. So I'm going to use synthetic substitution twice, because I have to go down from a quartic, 4th degree, all the way down to a quadratic. So the first, and it doesn't matter which one you use. You're going to get the same result when you finish, regardless of which one you use. So because I put -4 first, I'm going to use it first. So I synthetically divided with -4. That gets me new coefficients. And then I'm going to use the other. So I already used -4. The only way you can use a 0 again is if it's a double root. And it's not this case. When I looked at the graph, I didn't have any bouncing. So I have to use the other one, the one I haven't used, which is 2. All right, so this gives me my quadratic 2x squared minus 7x plus 3. And now I'm going to use the quadratic equation to find my other zeros. Quadratic formula is -b plus or minus the square root of b squared minus 4ac all over 2a. And you're just simplifying. Right here? Oh, you're right. I was wondering why it was factorable. It shouldn't be. Okay. This one. Well, yeah, that fixes the problem I was about to have, because it was about to factor, and I was like, that is not supposed to factor. All right, so it's minus 12. Oh, that's much better. 7 plus or minus 37. 37 is prime, so it doesn't break down, which means I can leave my two answers just like that, since it doesn't break down, nothing simplifies. Are all okay?
Would it still be 2, or would it be 2 on the bottom or still 4?
Oh, you're right. No, it's still 2 because it's, no, you're right, it's 1. It's 2, I mean, 2 times 1, so you're right. 2 times 1, which is 2. You're right. All right, is everybody good? So, does everybody understand that if you can get all of the zeros from your calculator and then be rational numbers, then that is all you have to do. But if you get a nasty decimal on one of them, or you look at it and it does not cross on a grid line, and it's not 1/2 or 1/4 or something nice like that, you have to use the quadratic formula. So you got to synthetically divide.
Why'd you take out the 2 of the?
It's not 2, it's 1.
Because it was 1. Because I didn't do it right. So I've only did this only the 3rd time I've done it today. You would think I would get them right.
I'm tired.
You should have told me that from the start. And I didn't know that. Hey, call me this morning. Hey, you didn't
Oh,
give me
shoot.
anything.
I couldn't send it.
I've never seen it before. Stay good.
Gonna do it, boy.
Oh.
Yeah.
Mullet?
4 problems.
My brother got one. I said, you should get a mullet. He said, I would never get a mullet in my life. And he sat there and got a mullet.
Do it.
Do it, Bryson. Bryson, let me get a mullet. Because he wants to be like the kid that's so my